Okay, so we're going to talk about what a square matrix is, and we're going to look at our inverse of a square matrix. Remember, square matrix is the same number of rows and columns. So a 2 by 2 is a square matrix. A 3 by 3 is a square matrix. 4 by 4, 5 by 5, 6 by 6. And we're only finding inverses for those matrices. Well, an inverse is really special, so let's take a look at this problem. So let's say we wanted to show that the following matrices are inverses. So we're going to go ahead, we're going to multiply them. Remember, we talked about multiplication as the combination of the rows of the first matrix and the columns of the second matrix. So if I were to expand this out, it would look as follows. So if I were to expand it out, I would get the following, and then we want to go ahead and simplify it, and we're going to get the following. Here we get positive 8. And here I get negative 7, which gives me 1. Here I get 4, and negative 4, which gives me 0. Here I get negative 14, and 14 gives me 0. Here I get negative 7 and 8, which gives me 1. So when I end up with the following, this 1, 0, 0, 1, that means they are true inverses. I end up with the identity matrix. Remember, an identity matrix looks like this. I have that 1, 0, 0, 1 for a 2 by 2. Remember, the main diagonal is always 1, so if I had a 3 by 3, it would look something like this. That would be if I multiplied two matrices together and got the following, and I got this matrix here, they would be inverses. Same thing with a 4 by 4, my main diagonal would be all 1s extended to here. Everything else would be 0s. So here the order of multiplication does not matter whether I have done A times B or B times A. I will always end up with the identity matrix if they are inverses. Okay, so take a moment and try this example. Okay, and this is what you should end up with when I combine the first row, first column, first row, second column, second row, first column, second row, second column. We do end up with 1, 0, 0, 1. Okay, so if a matrix has an inverse, then A is called invertible or non-singular, and if A is called otherwise, it's called singular, meaning it does not have an inverse, so that is possible. So specifically, it's either going to be invertible or it's going to be singular, meaning I cannot invert it or not invertible. So let's find the inverse of this matrix. There are a few methods that we're going to talk about how to do this. So this first method is going to apply to every single type of matrices, whether it's 2 by 2, 3 by 3, 4 by 4, etc. So we're going to use the Gauss-Jordan method. We're going to take the given matrix, and we're going to create that 1, 4, negative 1, negative 3 here. And just like in the Gaussian method, we had an answer column, but here I'm going to have an identity matrix instead to the right of that. Well, the identity matrix for 2 by 2 is 1, 0, 0, 1. And our goal is to manipulate this side to get the identity matrix here and then end up with the inverse here.
Is that an augmented matrix?
All right, so the first thing I want is a 1 here. I already have a 1 there, so I'm good to go. Now I want a 0 here in the Gaussian method. So if I add these two rows together, I'm good to go. So I'm going to say row 1 plus row 2 for that second row. So this stays the same, 1, 4, 1, 0. When I add them together, I'm going to get 0, 1, 1, 1. So notice that I'm almost there. This is 1, 0, 1. So my main diagonal here is 1s. The last thing I need is a 0 here. So if I multiply row 2 by negative 4, add that to row 1, then this becomes a 0. So let's go ahead and do that. So we're going to say negative 4 times row 2 plus row 1. And if you want, you can do the arithmetic out to the side. So we're going to say 0, negative 4, negative 4, negative 4. And we're adding that to 1, 4, 1, 0. And we're going to end up with 1, 0, negative 3, negative 4. So let's rewrite our new matrix here. 1, 0, -3, -4, 0, 1, 1, 1. So on the left now, I have my identity matrix, which is what I wanted. On the right is the inverse matrix. So we would use this notation to note the inverse of matrix A, which is -3, -4, 1, 1. Okay, so to confirm that these are true matrices, what I could do is I could take the given, right, this 1, 4, -1, -3, and multiply it to the answer. If I end up with the identity 1, 0, 0, 1, then I know they are true inverses and I did my work right. So this is the first method. We're going to call that method 1 the Gauss-Jordan method. All right, so now we're going to try a different method for the same matrix, but this method only works for a 2 by 2. And what we're going to do is we're going to take our matrix and let's label the elements A, B, C, and D. If I have a 2 by 2 matrix that have those elements, A, B, C, D, then I can use the following formula for the inverse. If I have a 2 by 2 matrix, then I can use the following formula. Okay, what we're going to do is we're going to find the determinant value. Basically, we're going to take this diagonal, multiply A times D. So whatever these two numbers are, we're going to multiply them. Then we're going to take these two diagonals, this other diagonal, B times C, and I'm going to multiply those two together. When I take the difference, we call that the determinant value. If I take the ratio 1 over the determinant times, notice that I swapped A and D and gave opposite signs to B and C. If I do that, then I end up with the inverse. And again, this only works for 2 by 2. So let's go ahead and find the determinant value for matrix A that's at the top. So I'm going to do -3 times 1 is -3. Minus 4 times -1 is -4. So my determinant value conveniently is 1. So therefore, I only have to do the swap and the sign change, and that's my answer. So the inverse to our matrix is 1 times swap -3 and 1, and sign switch to -4 and 1. So that's our answer. Notice that we get the same thing we got a moment ago. So I'm going to do the ratio 1 over the determinant times A and D swapped, B and C sign switch. So let's go ahead and use the formula on A and B. So pause the video, try it, and then continue playing it. Okay, so remember, the first thing we want to do is we want to find the determinant value. So we did 3 times 2 minus -1 times -2, and I'm going to get 4. So our formula said take 1 over the determinant, multiply it to, make sure these swap. I did. I put the 2 and the 3 here, and then these sign switch. So the -1, 1, -2, 2. So once I get to this step, then I'm going to multiply everything by a quarter. 2 times a quarter is a half. So I get that here and here. And then 1 times a quarter is a quarter. 3 times a quarter is 3/4. Let's take a look at what happens to B. I'm going to take my diagonal, 3 times 2, and I'm going to subtract it to -6 times -1. So that's 6 minus 6, and I get 0. Notice that I have to do 1 over 0 times the swap and the sign switch, but I can't do that. So this is an example of when a matrix would be not invertible, right, or a singular matrix. So not invertible. So let's find the inverse for the following matrix. So let's set it up first. All right, so here's the setup. Again, you're going to put the given on the left, you're going to put your identity matrix on the right, and then you're going to manipulate the left to look like the identity matrix. So the first thing I'm going to do is I'm going to divide everything in half. Okay, really important tip, do not interchange the rows, okay, because it's particular to this matrix and this matrix alone. So when I go ahead and I divide everything by 2, it's going to look like this. When we take a half of row 1, we get the following. The next thing I want is a 0 in this position, so if I add these 2 rows together, I'm going to get that. Okay, when we add them, we get the following. 0, 1, 5 halves, a half, 1, 0. The next thing I want is a 0 in this position, so if I multiply the top by -2, add it to row 3, I'm going to get a 0 here. Okay, when we do that, I went ahead and I did a little work on the side. So again, I multiplied row 1 by -2. I'm adding it to row 3, and I'm getting the following. The next thing I want is a 0 here. So if I multiply this row by 2, add it to this row, I'm going to get what I want. Right, when we do that, we get the following, 0, 0, 3, 0, 2, 1. I went ahead and I did the work on the side. So again, we multiplied row 2 by 2. When I multiply this by 2, I get the following. And then I add it to row 3, and I get the following. And the next thing we want is a 1 in this position, so I'm going to divide everything here by 3. And we would get the following. The next thing we want is a 0 in this position, so if I multiply this row by -5 halves, add it to this row, I'm going to get my answer. Okay, and we would continue the pattern here. You're going to do the same thing here, multiply this row by -3 halves, add it to this row, and you'll get your final inverse matrix. So I'm going to go ahead and just skip to the answer. And when you go ahead and you actually complete those operations, you get the following matrix.